Yes, because this research began here in Pisa in 2019, so before the pandemic, and the first discussion we got here were about the fourth paper, which I'm going to present today. But when we begin to write this paper, which is, by the way, is not still finished, we discovered that we need a lot of stuff, and it took more than 3 years to write the first 3 papers, and because we need the material in order to be able to do the result, which I'm going now to present. Okay, so as I wrote, the idea is to build up a thermodynamic formalism for dynamical systems which are perturbed in what we call a quenched way. I will explain in a moment what it means, and also when the system is could be open. I will show you what it means. Okay, all these papers are written in collaboration with these Australian guys, Jason Etnip, Gary Froiland, and Cecilia Gonzalez-Stockman. Okay, so let's start. It's very simple, the presentation, because if you didn't see yet what these quenched dynamical systems are, it's just a very short presentation. Some probability space, in any probability space, some map from the interval itself. Okay, something a little bit annoying. Formed, done, not completely in some sense, or when we restrict to the interval. If we try to get, for instance, to diffeo in any dimension, we have a lot of difficulties. This is just a very appealing and interesting subject. Try to generalize what I'm going to say to diffeo, for instance, even with singularity. Anyway, for the moment, we restrict to the interval, and as soon as we have this kind of maps, we can concatenate them, right? So we start with one map, or we concatenate with another one, and we get composition of this map. This is why the randomness arises, in some sense. Let me give you 2 examples how we can build this kind of random maps. We can take, for instance, as omega, the circle, and the map acting on the circle is the shift, I mean, the irrational rotation. And then what we do, we take a partition of the circle into a finite number of subset, and for each omega in this subset, we associate a map, which is constant. And then we compose in this way. Okay, I did a picture later on, which is this one. So this is the circle. We have a partition of the circle. These are the elements of the partition. And when omega is in one of these partitions, we associate to this omega a map. So this map is the same for all the omega into this set. When we move with the shift, with the rational rotation, and we go to this point here, for any sigma omega here, or for any omega here, if you want, we have another map. And I will tell you later on, very briefly, what kind of map we are considering. For the moment, it's not important. And okay, another example is more appealing in some sense. So we take a certain number of symbols, and we take the bilateral subshift. Here is the shift, not the subshift. You can easily the shift on this set, and so you see one element, one word in this set, in this space is this just a sequence of letters. Here we have L, and then we associate to each of these infinite sequence a map in this way. First of all, we associate to each of these symbols a map, and then we take for any omega, T omega is just the map which is associated to the 0 entry of this word. So for instance, in this case, to this number here. So when we get a composition of this map, just using this way to associate to omega map, we can follow the sequence of letters in this word. T omega 0, T omega 1, T omega n minus 1. So basically, this is just a way, there are several of these possibilities, to create not an interrupt of a map, because this is usually what we call a deterministic system, but a random system, because the choice of this map are doing, looking at, if I can go back, we choose this, oh, I'm sorry, we choose this, omega according to the distribution M. This is why we call it a random dynamical system. Okay, now, okay, since we have now the maps, all this map acts on the interval, okay? Now we define observables, because we are doing some kind of statistics, and observable depends, if you want, on two variables. The randomness, omega, which means we study this observable in a random environment, and then, of course, the point x, which is the point in the space. And when the times go on, so when we iterate, even the environment changes, because we pass from omega to an environment which is characterized by omega to an environment which is given by sigma omega, and so on and so forth. So the environment changes with the time, and when the times go on, even the point on the interval will move according to the concatenation which we choose. Okay, this is more or less the setting we are looking for. Okay, now what is an open system? Now there are two kinds of open system which I am going to explain. The first is real open, means we put an hole into the phase space. In our case, the phase space is the interval, and as you see, this hole changes with the random environment. So for any omega which fix the environment, I have different holes, which can be, of course, around different points. And then there will be another kind of hole. I will come back later on this hole, which I call the fake holes, because they're not real, but this hole will allow us to do, for instance, to study some statistical issue, in particular the extreme value theory and the recurrence. I will speak about these fake holes later on. Okay, now let's come back to the real hole. When you have a real hole, it means when points go into the hole, it disappear. So it makes sense to speak about what are the points which will not disappear when we iterate them infinitely often. And this gives rise to what we call the surviving set. So there is a surviving set up to time n. So all the points which are not, which didn't go into the hole from 0 to n. Look that when we iterate according to the random maps, the random composition, we are just going to the hole in a different random environment. I will give a picture in a moment about what it means, this one. And then if we take the intersection over all the surviving set at a fixed time, we get the global surviving set. Of course, it is a good question. What is epsilon here? Epsilon is the size of the hole. And for technical reason, if you want to do if you want to get rigorous result on this matter, it's very important if the hole is big or small. I will tell you in a moment later on what means this. Anyway, we can do, and you can do rigorous. Oh dear. Okay. No, but I will not use it. We can do rigorous result in both cases, with small and big holes. Of course, the result with small holes are more interesting because you can get much more information. Anyway, let me give you just a picture of what I mean when I say that we change the random environment. There is another way to look at this system. You can find all the information in Arnold and Kiefer books. Instead of keeping the interval, we can keep copy of it. I mean, for any omega, we associate a copy of the interval, and these are called fibers. And you see, for each omega, we have a fiber, and we put the holes on each fiber. So instead of moving a point from one point of I to the other, to the iterate, we can move the point from one fiber to the others. Okay, so this is another way to understand what I mean by random environment. The random environment characterized by fibers, which could be the same copy of the interval or something different. In this case, are all the copy of the same interval I. And this is called fiber dynamics in our notebook. Okay. Now, since we put holes, the question is, what is the measure which we put on the system? Since we are doing ergodic theory, we need measures. And we see now there is a festival of measures from now on. I'm sorry, but they are a little bit difficult to construct, but they are essential. The first measure which we need when we have an open system is what people call conditionally invariant measure, but in this case we have randomness, so we have to put another adjective in front of them, and we call them random conditional invariant measures, and they are defined in this way. I prefer to define it in this way. Take a set A on the fiber sigma and omega, right? The measure of this set is exactly equal to the image of this set in the fiber omega divided by the measure, if it exists, of the surviving set up to this n. Okay? So this measure takes care of the fact that we have holes, and it avoids hole just by adding this factor here. And this is the measure which are usually, which we want to use to study the system with holes. Okay, now how can we choose this measure? Okay, first of all, the measure which I'm going to choose are measures of this type, which are also absolutely continuous with respect to some other measure, which I'm going to construct. Then there are other measures which are important in this setting. The first one is the measure which lives on the surviving set. If the surviving set is not empty, it happens, it could bring some measure, okay? And this measure, I put an infinite here. Look, this measure has nothing to do with this one, apparently, because this measure could be supported on a large set. Usually, these are supported on very small and fractal set. And then there is another measure which will play a role in the following, which is the measure which lives on the set without holes. So I have a set, I don't put any hole, I have an invariant measure. Sorry, invariant measure is a little bit misleading because here we are in a random setting. These measures are called equivariant in the language of random setting. But okay, let me call it invariant. Anyway, it's a good measure for what we are going to study. In the next slide, I begin to construct this measure very briefly because this became technical. But if you work with this method, you know that this measure arises as eigenfunction of a certain operator, which is the famous Perron-Frobenius operator. In this case, the operators are defined on this random setting. So you see, each of these operators depends on omega. They are defined in the usual way, where this guy here is called the potential, and this is the observable, which could depend on omega as well, by the way. I didn't put omega, but it could depend on omega. And this operator acts on some space. The space also is a Banach space. There is an index which is still, it depends on omega, which is the random variable. And then this is just the iterate of this operator, and here is the iterate of the potential. Okay, so now you see, this operator are important because we define all the set of measures which I introduced before thanks to this operator. In particular, this operator, okay, when I put 0, it means we take the system without the hole. So what we call the closed system. There are no holes. It's not open, it's just closed. And associated to this operator, there are two objects. The first are this multiplier, lambda omega 0, and then there are measures. The multipliers and the measures verify these two equations, and phi here is just a density, an element of the Banach space. Okay, so this is the usual scheme. And when you have this object here, we can construct what I call the invariant measure for the random system, which is just a measure which verifies this property here, which is called the equivariance property, is very, very similar to the property verified by an invariant measure. But the difference here is just you integrate with respect to a measure on some omega, and you go to the iterates of this measure. Because we don't have any invariant measure, we have a family of measures which verify this equivariant property. So this is one of the measures which we saw in the previous slide. It came as the product of the eigenfunction of the operator and the dual, as usual. Then we put then we put the noise. The noise means I take a perturbed operator, which is the previous one, but restricted to the complement of the whole. This guy is the complement of the whole. So this induces some sort of perturbation of the previous operator. Okay? And now, when I wrote suppose, it means we have to prove all this. Okay? So it's not obvious what is written here. It took, as I said, it took 3 papers when we begin to do it from 2019 up to this year to prove all this. In particular, what takes a lot of job was, in the previous transparency, was to prove, to prove this one. It took 2 here to prove the existence of this object here. No, of this one. Of this one. Okay, anyway, when you take the perturbation, then we can do the same. So we can prove the existence of these multipliers, of these measures, and of these densities here. And we construct other measures. In particular, the measure which lives on the surviving set, the global one, is just the product of this measure, which is the conformal measure for the open system, times this density. And it turns out that the conditional invariant measure, which I introduced 5 minutes ago, is just absolutely continuous with respect to the conformal measure for the closed system, but when multiplied by this density here. It's a little bit strange, right? I mean, it's not completely obvious to me. I mean, this holds anyway in the deterministic setting. The deterministic setting, all this theory was given by other people, Carlangelo and Veronique Mohm, and we generalized it to the random setting. More or less, we have the same scheme. Okay, now we have all the measure we need. Then a few words about the map. So the map are defined, okay, this is not the more general class of map which we consider, okay? But just to give an example, our map of the intervals, which are defined out of countably many subsets where they are monotone. We have, finitely many branches. This is the condition of finitely many branches. We don't have expanding properties, if you look carefully, but we replace the expanding properties. This is just the derivative is finite. There's no larger than 1. But we replace the expanding properties with some covering assumption. So it means if you take some interval, right, you can find an iterates which expand sufficiently fast the interval. As a potential, this is just an example, but we have a full class of potential. We can take the geometric potential with some beta here, which is different from 1. So this is the setting. But I said this can be much more general. And then the first formula is about the escape rate. Okay, so since we have a set here where the points stay up to the time n, the question is, how do we have a rate for this surviving set of points? And the answer is yes. This is the first result. This is just the difference of the integral of the 2 multipliers which I introduced before. This multiplier depends on the noise, so for this reason we integrate with respect to the distribution of the noise. And then, okay, we can also prove that these guys are coincide with the pressure, okay, but I'm not going to define it. What happens when the size of the noise goes to 0? It is interesting because this number here, which is called the escape rate, we have also a formula when the size of the noise goes to 0, and this is the formula. And this object here is an object which comes several times in this method. It has a name, it's called the external index. It was, first of all, for the first time studied by people doing extreme value theory, and then we discovered it is also related to this asymptotic behavior for the escape rate, for instance. I will come back in a few minutes on this. Please tell me when I have to stop, how many time I have.
5 seconds.
Good, very good. So I go a little bit faster. And okay, so let's now, in order to describe what this number is, let's go to the fake calls. So the fake calls allow us to introduce what is called the extreme value theory. Basically, you have an observable which at a certain point, in this point, which at a certain point assume an infinite value. And this infinite value, I call it Z omega bar, right? And then I take some Z omega, which is less than, which is finite, and I look, this is a known, I look to all the points where this observable, in this point, is larger than this value. So you see, it's just a neighborhood of the points where this function jumps to infinity. And then I take a sequence of these values which are approaching the infinite, right? And I look to this distribution. So I take my observable and I look at the probability that the observable on the fiber omega is less than this first number. When I iterate observable, so in another point, is less than this other threshold, and so on and so forth up to time n. So this is the typical distribution which is studied in extreme value theory. And the question is, do we have some asymptotic distribution when n goes to infinity? And the point is, this question is not very well posed because it happens that if we don't choose this threshold in a good way, this distribution could be degenerate. So for this reason, there are some way to fix it. Okay, this way to fix it is very well standardized in the extreme value theory. So if you do this method, you will see that we have to have some formula for the asymptotic form of this all. In our case, it turns out that we choose this one. And if you choose this one, namely, you see, this is just the measure of all. The measure of all depends on the choice of parameters plus some error divided by n. N is the time to which we have iterate when we look at the all at time n. If we have this scaling, what we get is this result, which is the quenched form for the extreme value theory. Now, what is interesting is the previous scaling here, we can get in some sense, not for free, but it is suggested by the theory which we use to prove this result, which is a theory which was developed, we use a perturbation result which was developed in the deterministic setting by Keller and Ivarani. Keller studied this kind of property in the deterministic setting, and we were able to generalize it in the random setting. And this kind of condition came naturally from the technique. So the certain point, the techniques tell you you have to use this one if you want to get some result. And in fact, we get this theorem. And you see, now we meet for the second time this famous object here, which is the external index, which has a formula. The formula is given by an infinite series, and the elements of this series are this horrible object. But it turns out that this horrible object can be computed exactly on examples. I mean, not all the examples, but there are a lot of examples where we can compute exactly this. I give you an example in a moment. You can compute exactly this object here. Just to go faster, one of the most studied observable in this matter is this one. So basically, it gives the distance of your point from a fixed point x. Okay, so you see, if you take this kind of observable, the all is just a ball. It's a ball around a point, y, of some radius, which depend on some number n, but it's random, so it depends on the fiber which you choose. And then you can introduce, and this is another topic which is related to what people call first sitting times. We can study the first time these random iterators of a point jump into a ball, which is on some fibers, but all the edges of this fiber are indexed by n. And we are just looking to the distribution of the points where the heating time is bigger than something, normalized by the measure, of course, of the first ball. Otherwise, we get some degenerate. And even in this case, we have a result. Okay, so we go to the exponential heating time statistics again, modulated by this number, which is called, again, the Semmel index. There is an error here I discovered before the talk. It's not n here, it's just the measure of the set. Sorry, this is not n, because this number must go to infinity, not to 0. Let me give you, in the minutes which are left, an example, because you could ask if there are examples for all this. The question is, there are very simple, unfortunately, because it's very difficult to find examples which satisfy the 10 al 11 assumption which we have in order to get all this working. But, I mean, anyway, the example is very simple, by the way. So, okay, we take this observable here, and then we take, I take an alphabet of 4 letters, and to each letter I associate a map, so T0, T1, T2, T3. Then I take balls. The radius of the balls is random. It depends on omega. Omega is just a sequence of letters in this alphabet here. And there is a grammar now, namely the choice from one letter to the center of the ball should satisfy a certain number of properties which are written here. So the idea is to avoid periodicity, apparently, because this number θ0, which I call the external index, it is associated naturally to cluster phenomena, which comes when we have periodic points. But here we don't have periodic points, which is only a random setting, and in particular evident from the choice of this center. Okay, so now if you make the machine starting with concatenation of maps chosen, okay, the map here are chosen as Bernoulli map in order to get rigorous computation, but they can be expanded map of the interval. Of course, different because I have 4 maps. You see, the fake cost, so the balls, changes the location and also the radius, because also the radius can be random. And we have to follow this grammar in order to get something interesting. And we can compute exactly this object here. We can compute them. We computed, of course, the first 2, because they became very complicated. And the first 2 immediately imply that the number which I call the XML index is not 1, so it means we have cluster effect. So it means the random orbit tend to spend a lot of time in some place instead of going uniformly everywhere. Okay, I finished now. Thank you very much.